begin this video by reminding ourselves of the graded structure of G3, the geometric algebra of R3. At the lowest level of the structure, we have the grade 0 elements, which are just the scalars. There's just one basis element there, just one. We have three vectors in R3. These are going to be the three grade 1 basis elements here, the three vectors E1, E2, and E3. Next up, we have the grade 2 elements, the bivectors, also called the pseudovectors, which are formed by taking two vectors at a time, two of the three vectors at a time. So we get three possible combinations there. So we have E1, E2, E2, E3, and E3, E1. Then finally, at the highest level of the structure, we have the pseudoscalar, the single pseudoscalar, which is formed by taking all three vectors at once, which is E1, E2, E3. So in total, we have 8 basis elements in this abstract vector space. Now remember, in the last video we were talking a bit about rotors. Now what is a rotor? This is the geometric product of two unit vectors, that is to say two vectors of length 1. Now where in this algebra does a rotor reside in terms of the graded elements that it's going to contain? Now because it's the geometric product of two vectors, it's going to contain a scalar or grade 0 element formed by the dot product between the two vectors, and a grade 2 part, which is formed by the wedge product of two vectors. Now this is the usual way we write the geometric product of two vectors. Remember, you can also write it in this way. The length of u times length of v times e to the theta b hat, where b hat is the unit bivector in the u wedge v plane, and theta is the angle from u over to v, and these are just the lengths of u and v. Now in the special case where both these are of unit length, this will just be e to the theta b hat. But this is always going to contain grade 0 stuff and grade 2 stuff. And because it's only going to contain elements of even grade, notice these are just the even graded elements here, the grade 0s and the grade 2s, we're going to draw our attention to a specific subset of G3 called the even subalgebra. So the even subalgebra. So this is just what the name says. It's the subalgebra, the subset of this total algebra, consisting only of the even graded elements. So what we're going to do is, instead of considering any possible linear combination of the 8 basis elements here, we're going to only consider linear combinations of the basis elements which are of even grade. And you can see here there are 4 of those. We have 1 scalar and 3 bivectors. So there's going to be some linear combination of the scalar. It's going to have a scalar part, and it's going to be some linear combination of these 3 basis elements dealing with the bivectors. So the most general element of the even subalgebra of G3 is going to look like this. It's going to be some scalar, we say little a, plus some linear combination of the bivectors. So b, another scalar, times e1, e2, plus c times e2, e3, plus d times e3, e1. You can see the grade 0 over here, and from here to here, the grade 2 part. And you can see there are 4 coefficients here in front of each one of the basis element. We have a, b, c, and d. Therefore, the even subalgebra of G3, which we're going to notate in the following way. So it's going to be G3, but to signify the even part of it, I'm just going to mark that with a plus sign. So this is the notation we're going to use for the even subalgebra of G3. This even subalgebra is going to be of dimension 4. As if we consider it as an abstract vector space, it's going to have 4 basis elements. It's going to have the singular scalar and 3 basis bivectors. So it's of dimension 4. Which, if you notice the title of this video, the Quaternions, this is going to have something to do with the Quaternions, because I claim that this even subalgebra is in fact isomorphic to the Quaternions. It has the same structure as the Quaternions. But before we start talking about the Quaternions, I'd like to first note something important about this even subalgebra, namely that it is closed under the geometric product. That is to say, if you take two elements that are both in the even subalgebra, multiply them using the geometric product, what you get back out is yet another element of the even subalgebra. That is to say, this is closed under the geometric product. And that can be seen very simply just by inspecting the possible multiplications that can be done with the basis elements of something within the even subalgebra. Because you can there are only a few possibilities. You can multiply a scalar times a scalar, which gives you another scalar. You can multiply a scalar times a bivector, which gives you another bivector. Multiply the bivector times a scalar, which gives you another bivector, another grade 2 element. Or you can multiply a bivector times another bivector. Now, within that, there are two possibilities. You can have the same bivector being multiplied by itself. Remember, each one of these bivectors will square to minus 1, in which case you get a grade 0 term, so it's closed there. Or you can have a bivector basis element being multiplied by another one, by a different one, in which case you get plus or minus the third one. For example, if I multiply E1, E2 times E2, E3, what I get is E1, E3. Remember that E2 squares to plus 1, which is just a negation of this one. So you stay within the grade 2s. Or if you multiply E2, E3 times E3, E1, what you get is E2, E1, which is just a negative of this one. And the same thing for the other possibility as well. So you see that whenever I multiply two things within the even subalgebra, what I get back out is another element of the even subalgebra. So this set is closed under the geometric product, in other words. That's important to note because that's what allows us to make sense out of talking about an even subalgebra as a closed set. So as I said, the even subalgebra, G3+, it's going to be of dimension 4, considered as an abstract vector space. Let's yank out those 4 basis elements. So I have that singular scalar, which is just represented by 1. I have E1, E2, then E2, E3, and finally E3, E1. So this would be the basis for the even subalgebra of G3. Now let's take note of the algebraic features that we already know from previous videos. We know that each one of these bivectors, these basis bivectors, E1, E2, E2, E3, and E3, E1, each of these squares to minus 1. Let me write that out in a perhaps suggestive way. So E1, E2 squared is equal to minus 1. And so is E2, E3. That also squares to minus 1. And so does E3, E1. That also squares to minus 1. Now E3, E1 squares to minus 1. E1, E3 also squares to minus 1. Now, take a look at this times this one. E1, E2 times E2, E3. What does that give us? We have E2 squared there. That's just equal to 1. So we're left with E1, E3, which is also equal to minus E3, E1. So what I get is one basis element times the other, giving me a scalar multiple of the remaining one. Now check this out. Suppose I renamed these 3 basis bivectors in the following way. Let me take E1, E2. Let me call that I, little I, not to be confused with big I, which is the notation I'm using for the pseudoscalar E1, E2, E3. Let me name E2, E3 little j. And let me take this E1, E3 and call that k, which, by the way, that's equal to minus E3, E1. Equivalently, E3, E1 is going to be minus k in this scheme. And let me rewrite this upper line here. So I have I squared is equal to j squared is equal to, remember I said E3, E1 is going to square to minus 1, but E1, E3 is also going to square to minus 1. So this will be k squared is equal to minus 1. And I have down here I times j is equal to k. I times j is equal to k. Now, if you wanted to set all of the stuff equal to minus 1, you could do the following. You could take this equation, multiply on both sides on the right by k, in which case I have ijk equals kk, or k squared, but k squared is equal to minus 1. So I have minus 1 over here. So you could add that all in to one singular equation. Now, what is this equation here? This is the defining equation of the quaternions. So what we've discovered here is that the four basis elements of the even subalgebra, 1 as the scalar, and then E1, E2 is the first bivector, E2, E3, and E3, E1, or minus E1, E3 if you prefer, but it doesn't matter because those are just the same up to a scalar. What we've discovered is that this basis of the even subalgebra is also a basis for the quaternions too, and that these algebraically function in the same way as the quaternions do, and that you have three things here, three bivectors, each of which square to minus 1, which is the same thing that the i's, j's, and k's are doing in the quaternions. Those are all squaring to minus 1. And you additionally have that one bivector times the other, the I, the j, gives you k when they're multiplied together. Here, this was I, this was j, this is actually minus k, but k is just E1, E3, but the same algebraic structure is present here. That is to say, the even subalgebra of G3 is isomorphic to the quaternions. Quaternions are just symbolized by the letter H, H for Hamilton, based on the guy who discovered them. Which is to say that you can translate back and forth between the set of things within the even subalgebra of G3 and the quaternions, preserving their operations. You can do stuff using the geometric product when you're working in this set, and you can just as well do operations using the quaternion product, using i's, j's, and k's in the set of quaternions. You can go back and forth, preserving their algebraic structure. Now, when we establish an isomorphism between these two sets, we might just say that they just are the same thing. They're the same thing going under two different names, going under two different notations. And because of that isomorphism, you might hear me say that the even subalgebra of G3 just is the quaternions, or is the same thing as the quaternions. And speaking in terms of the algebra, they are the same thing. Now, that correspondence, that going back and forth between the even subalgebra and the quaternions, is done in the following way. If I have some general element of the even subalgebra, let me say A plus B E1, E2 plus C E2, E3 plus D E3, E1. This is an element in the even subalgebra. I can send that over to the quaternions by doing the following, just translating the symbols. I associate with the following quaternion, A plus BI plus CJ, now minus DK. Now I've got to add in that minus because remember E3, E1 is actually minus K, not K. So I translate the elements of the even subalgebra into the quaternions in the following way. And this function going from here to here is called the isomorphism. And you can go in the reverse direction too. If I have something that looks like this in the quaternions, I can translate that over to an element in the even subalgebra in the following way, just keeping these coordinates the same, just flipping sign on this last one here. Now what's pretty neat about this is that if you have a second element in the even subalgebra, let me say E plus F E1, E2, G E2, E3, plus H E3, E1, where the A through H, those letters are just scalars. Those are just the coefficients sitting out in front of the basis element. This too can be sent over through the isomorphism to a corresponding quaternion, which is done in the similar way up here, just keeping E, F, G, and flipping the sign of the H there. So this would be the quaternion E plus Fi plus Gj minus Hk. Now what the isomorphism allows me to do is that, suppose I wanted to multiply this thing, this element of the even subalgebra, by this one. Let me give this a name just to make it simpler. Let me call that R1 and R2. Suppose I wanted to carry out the operation R1 times R2 using the geometric product. I can do that. That would also be the same as associating this to its corresponding quaternion, which I'll name Q1, and associating this R2 to its corresponding quaternion, which I'll call Q2. carrying out the product over here in the quaternions using the quaternion product, using the rules associated with quaternions, such as I times j going to k, and so forth, making sure each one of these i's, j's, and k's squares to -1. I can carry out that operation, get a quaternion over here, and then translate that back to an element in the even subalgebra, and those two processes are the same. Those are the same both for doing the geometric product and also for straight up addition. Addition is very easy to see. Let me say that one more time just to make that absolutely clear. These two processes are the same. If I take R1 and R2, two elements of the even subalgebra, generate a third element of the even subalgebra called R3, which is just a product R1, R2, where the product here is a geometric product, then translate that over to the quaternions, the associated quaternion, which I'll call Q3. That is the same as this process. Mapping this over to its associated quaternion, which is called Q1, mapping this over to its associated quaternion, Q2, and performing the product over here, Q1 times Q2, where this product is the quaternionic product, or the Hamilton product, and getting Q3 out of that. So those two processes are the same, and you can go back and forth between this and this. But the whole point of this is to preserve the algebraic structure of the even subalgebra with the set of quaternions, which I'm saying are just, they just are the same thing algebraically. Now, people who watch my channel probably know quite a bit about quaternions already because I make videos on those, but supposing you didn't know about quaternions, here you go. A quaternion is just something that looks like this. A plus bi times cj plus or minus dk, just some coefficient out front there. But because you know how to multiply bivectors, for example, multiply e1, e2 times e2, e3 to get e1, e3, you already know how to do the quaternionic product, basically. You just need to translate back and forth between the symbols. Just translate when you see e1, e2, move that over to an I. When you see e2, e3, move that over to a j. When you see e1, e3, move that over to a k. And in reverse direction. Suppose I asked you to compute the quaternionic product ki. Tell me what that's equal to using quaternions, just using i's, j's, and k's. Well, k, what is k? That's e1, e3. Going in this direction using isomorphism. What is I? That's e1, e2. Well, now we just shuffle this stuff around. Let me move e1 over there. So I swap there, that'll generate a minus sign. So I have e1 squared minus e1 squared times e3, e2, which is equal to minus e3, e2, which is equal to e2, e3. Now, what is e2, e3 in the quaternions? Well, that's just j. So there you go. You already know that in the quaternions, ki is equal to j. Just make the appropriate changes in notation going back and forth, and you know how to multiply quaternions if you already know how to multiply bivectors, which you do know how to multiply bivectors if you've seen the other videos. By establishing this isomorphism, an important algebraic feature of the quaternions is noticed immediately, which is that quaternions algebraically are behaving as bivectors, more generally scalar plus bivector. They are not behaving as vectors, which is often how you're treating them when you study quaternions on their own. You treat them as though they were some sort of augmented vector, or they have like a scalar plus a vector part. And when you do things like rotations, you try to focus on the so-called vector part of the quaternion only. Now, quaternions algebraically are not vectors. They are scalar plus bivector, and they are elements of the even subalgebra. And more specifically, these quaternionic units, the so-called imaginary units I, j, and k, these are not vectors, these are bivectors. e1, e2, e2, e3, and e1, e3. They're not vectors in the sense of pointing vectors like that. They're bivectors in the sense of wedge products and oriented patches of area. Now that's important to note because oftentimes people are very, very confused on what the quaternions are. They think that they're vectors in this sense. They're only vectors in that sense in a very artificial way. What they are in a more natural sense are bivectors. Now, when one studies quaternions, particularly in the setting of rotations, one is often interested in a very specific subset of the quaternions, namely the unit quaternions, which are those quaternions which are of length 1, or of magnitude 1. Now, I'd like to show how these link up with rotors, which are something we already have a bit of experience with. Now, to do that, what I'm going to do is consider some general element of the even subalgebra, of G3. Let me call that R. It's going to be A plus B E1 E2 plus C E2 E3 plus D E3 E1. Or you can just view this as a quaternion if you prefer, except with components A, B, C, minus D in our naming scheme as we've seen before. Now remember that the rotors had an additional very special feature, which is that R dagger times R and also R dagger were equal to 1. Now the dagger was just the reverse operator. Now what that means is that when you see a product of vectors, just reverse the order. That's what the dagger operation means. Now I'm going to use a dagger operation to see what happens when we apply this to a general element of the even subalgebra. What I'm going to do is rewrite this in a slightly different way. I'm going to write it as a scalar plus bivector. I'm going to rewrite it as A plus big B, where big B is just all this stuff from there to there. That's going to be B. So scalar plus a bivector part, just going to collapse it like that. Now, if that's what R is, what is R dagger here? Well, it's going to be A plus B, all dagger. Now, the reverse operator will distribute to each one of those two terms, so A dagger plus B dagger. Now, A dagger, the reverse of a scalar, is just itself. It's invariant under the reverse operation. So that's going to be just A. Now, what happens when you take a bivector and take the reverse of it? Now, a bivector is going to contain some linear combination of the E1, E2, E2, E3, and E3, E1s. Now, when you reverse one of those, let me just say E sub I plus E sub J. When you reverse that, what you get is EJ EI, which is equal to minus EI EJ. So when you have a bivector, the effect of the reverse operation is just to negate. So that what that means is that B dagger is really just minus B. That's the effect of that. Now, this is pretty interesting because in the quaternions, what one often does is consider the scalar part to be a sort of real part of the quaternion and this rest of the stuff to be an imaginary part. Now you can see when I look at this reverse operator, what it's doing is keeping the real part the same, but flipping the sign of the imaginary part. And that connects up to what I've said probably a number of times, which is that the reverse operator is a sort of conjugate operator, and that it will preserve the sign of the real part, but it'll flip the sign of the imaginary part. Now, we have our dagger here. That's just A minus B. Let's apply this property of the rotor, which is that R dagger times R is equal to 1. So let's consider R dagger R. That's A minus B times A plus B, which will be A squared minus B squared. So just the square of the scalar, then minus the square of the bivector. Now, in the video in which we dealt with bivectors in more detail, we noted that when we square a bivector, what we got is the minus magnitude squared of the bivector, where the magnitude is just the amount of area contained in that bivector, which means that minus b squared is just the squared magnitude of the bivector. So really I can write this in the following way. R dagger R, or R dagger if you flip the order here, it's the same thing. That's equal to A squared plus the squared magnitude of the bivector part, which is just the sum of squares of the components, which would just be B squared, C squared, and D squared. Now, with the rotors, that's got to be equal to 1. To write that in a different way, that means that A squared plus little b squared, this b up here, plus C squared plus D squared is equal to 1. Which is to say in these rotors that they are the elements of the even subalgebra such that the sum of squares of the 4 components, scalar plus the 3 bivector coefficients, the sum of squares of those 4 would be equal to 1, which would be algebraically just the same thing as a unit quaternion. That is, if you were to consider this as a quaternion, A plus BI plus CJ minus DK in our naming scheme, a unit quaternion would have the feature that A squared plus B squared plus c squared plus d squared is equal to 1. That is, its squared length is equal to 1. Now, if you've studied quaternions at all, particularly in rotations, this should make perfect sense, because within the quaternions, the things that do rotations only, without scaling the vector in any way, are the unit quaternions specifically. Those quaternions such that the sum of squares of the 4 coefficients is equal to 1. Now, in geometric algebra, the things doing the rotations, the mathematical objects that do the rotations, are the rotors. Those are the elements of the even subalgebra, such that r dagger times r, and also r dagger, those are equal to 1, which implies that the sum of squares of those 4 things, those 4 coefficients, are equal to 1. So we can see we can go back and forth between thinking of rotors and unit quaternions, and how the rotors in G3, these are just the unit quaternions. You don't need to study anything in addition. You don't need to do some sort of ad hoc study of the quaternions just to be able to do rotations in 3D. If you know about rotors, you already know about quaternions. You just know them under a different name. And now that we're talking about the relation between rotors and unit quaternions, I'd like to point out something else. In our study of quaternions, in those videos or in your own study, you'll know that if you have 2 unit quaternions, multiply them using the rules for quaternion multiplication, what you get out of that multiplication is yet another unit quaternion. That is to say, if I have 2 quaternions, let's say Q1, Q2, I get another quaternion Q3. If Q1 and Q2 are unit, then Q3 is also unit. This follows very simply from the fact that when you consider the squared length of the product, this is equal to the product of the squared lengths individually. So that if the length of Q1 and the length of Q2 are equal to 1, then the length of Q1 times Q2 is also equal to 1, just applying that formula. Now, something very analogous, well, algebraically probably the same, is true of the rotors. That is to say, if you take 2 rotors, multiply them together using the geometric product, what you get out is yet another rotor. We already know that if you take 2 elements within the even subalgebra, multiply them one by the other, you get another element of the even subalgebra. This is something more specific, that if you take 2 rotors, multiply one rotor by the other, you get a third rotor. That is to say, going back to this defining feature of rotors, that r dagger r is equal to 1. If I have 2 rotors, let's say r1, r2, then r1, r2 dagger times r1, r2 is also equal to 1. This is also very easy to see. In the last video, actually let me review this. A rotor is a product of 2 unit vectors. Let me say r1 is equal to uv, r2 is equal to wx. That means that r1, r2 is equal to uv wx. Now consider the reverse of r1, r2. That would just be writing this in reverse order, which would be x, w, v, u. Now check this out. Let me throw some parentheses just to make that clear. What is xw? Well, that's just r2 reverse. r2 dagger. What is vu? That's r1 reverse. And that's why I want to point out, when you have r1, r2 all dagger, that's equal to r2 dagger times r1 dagger. Now check this out. r1, r2 all dagger, we have r2 dagger, r1 dagger times r1, r2. r1, by assumption, is a rotor. Therefore, r1 dagger times r1 is equal to 1. Therefore, that's the same as r2 dagger times r2. r2 also, by assumption, is a rotor, which means that's equal to 1. So this is indeed confirmed. That is to say that the rotors of themselves form a group. They're closed. They have the associative property. They inherit that from the higher algebra. They have the identity, which is just 1. 1 is also a rotor. And they have an inverse, which is just the dagger. That fact that the geometric product of two rotors is yet another rotor has a very nice geometric interpretation. Remember, rotors are the things that do the rotating in geometric algebra when they're applied to a vector in the two-sided way. Now, applying a geometric product of two rotors in the two-sided way is a composition of two 3D rotations. So doing one rotation followed by another. Now, because the geometric product of two rotors is yet another rotor, what that means is that the composition of two 3D rotations is yet another 3D rotation, meaning that the equivalent rotation can be gotten by some other 3D rotation in a single step instead of going in a composite way, doing R1, then R2. Now, as an exercise, what I'd like you to do is just consider some general element of the even subalgebra called R, which is going to be written in the following way: E plus B, E1, E2, plus C, E2, E3, plus D, E3, E1. Now, let me define the magnitude. It's actually the squared magnitude of R in the following way: R dagger times R. Show that R1, R2, the squared magnitude of that is equal to the squared magnitude of R1 times the squared magnitude of R2. And when you show that, this shows an analog of what's going on in the quaternions, in that the squared length of the quaternionic product of Q1 to Q2 is equal to Q1, the magnitude of Q1 squared, times the magnitude of Q2 squared. So it's showing something very analogous, in which case this would prove the fact that a product of two rotors is another rotor would be a sort of special case of this formula, just as the fact that the product of two unit quaternions is another unit quaternion is a special case of this more general formula. So this is something interesting you might want to prove. Now, operationally, both rotors and quaternions are being used to do rotations in actual computations. So let's actually compare the formulas of rotations using rotors and formulas for rotations using quaternions. Now, recall what the formula for a rotation using rotors was going to be. If I have some vector v, we're going to operate upon v in a two-sided fashion. On the right-hand side, we're going to have e to the theta over 2, b hat. B hat is the unit by vector in the plane in which you want to do the rotation. Theta is the angle through which you rotate. And on the left, because we're operating in a two-sided fashion, we have the conjugate, which is going to be minus theta over 2 times b hat. So that's the rotor formula. So the output vector I'll call v prime. So this over here is for rotors. Now, if you check out my quaternion videos, or if you've studied this at all on your own, if you were working in the quaternions, you would treat v, but v is now a quaternion. It's not quite a vector, even though you're artificially treating it as a vector. Again, you're operating upon v in a two-sided way using quaternions. Now, that's also going to be a two-sided rule. On the left-hand side, we're going to have a quaternion, which is going to be e to the plus theta over 2 times n hat, where n hat is the axis of rotation. It's also going to be a unit vector. A vector in quotes, yet again, because you're actually treating this as a quaternion, not as a true vector in the geometric algebra sense of a vector. And on the right, we have the conjugate. We have e to the minus theta over 2 times n hat. And the output vector over there would be v prime. So this is what's going on in the quaternions. Now you can see, in terms of their form, these formulas are quite similar. They're both operating upon a vector in quotes over here, in a two-sided fashion. And the left and the right are sort of conjugates of one another, and that the arguments are being negated. And I can write these two in a more compact way. What I can do is call this thing, this exponential on the left, r, as I have done in previous videos, in which case the formula becomes this: v prime is equal to r times v. And then this thing, because this is being defined as r, this will actually be r dagger, the reverse rotor or the conjugate, if you prefer to think of it like that. So this is the formula in geometric algebra using rotors. In quaternions, what I could do is call this exponential on the left q, in which case the formula becomes v prime is equal to q v. And because this is being defined as q, this exponential on the right is actually going to be the conjugate, which I mark with a star, as you sometimes do in complex numbers too. And that's all for this video. Thanks for watching.